तो बच्चों, आज एक नया टॉपिक आपके लिए फिर से, और जैसा कि मेरा वादा है कि इतना आसान बना देना है कि एग्ज़ाम हो जाए केक वॉक की तरह। और टॉपिक हम कौन सा लेंगे? हमेशा की तरह इम्पॉर्टेंट टॉपिक ही लेंगे हम। ऑब्वियसली फिजिक्स में कौन सी ऐसी टॉपिक है जो नॉन इम्पॉर्टेंट है? ये फिजिक्स का टॉपिक है, लेकिन केमिस्ट्री में भी काफ़ी काम आता है। हाँ, एक बात और बता दूं कि ये एडवांस के लिए ज़्यादा ज़रूरी है, ना कि नीट के लिए। मेंस के लिए भी इम्पॉर्टेंट ही है, पर एडवांस में डायरेक्टली सवाल आपसे पूछे जा सकते हैं इस कॉन्सेप्ट से। टॉपिक है क्या? गेस कर लिया क्या? अच्छा, गेस नहीं कर पा रहे हो आज? कोई बात नहीं, मैं बता देता हूँ। टॉपिक है वेव इक्वेशन इटसेल्फ। तो वेव इक्वेशन क्या है ये हम देखेंगे, और आगे जाने से पहले कुछ बातें और बोल दूँ मैं आपको कि वेव इक्वेशन इतना इम्पॉर्टेंट क्यों है। क्योंकि ये मॉडर्न फिजिक्स का बेसिस है। आपके कोर्स में वेव्स चैप्टर है, एसएचएम भी है, साउंड वेव्स हैं, वेव्स ऑन स्ट्रिंग भी है। उसके बाद मॉडर्न फिजिक्स में अब जाइएगा तो वहाँ पर थोड़ी बहुत बातें होती हैं श्रोडिंगर इक्वेशन की। पर केमिस्ट्री में तो ये काफ़ी इंपॉर्टेंट है, क्योंकि आप क्वांटम मैकेनिक्स की बेसिस वहाँ पढ़ते हैं, क्वांटम नंबर्स की बात करते हैं, एटॉमिक स्ट्रक्चर की बात करते हैं। तो ये जो इक्वेशन हम डिस्कस कर रहे हैं ना, यही इक्वेशन बेसिस है आपके श्रोडिंगर इक्वेशन का भी, और बाकी जो सारे वेव्स हैं उसकी बेसिस है। तो आप साइंस के किसी भी डोमेन में चले जाइए, या तो फिजिक्स साइड में जाइए, मेडिकल साइड में जाइए, हर जगह इसका एप्लीकेशन है। तो इसको आप अगर अभी ढंग से सीख लेते हो तो आगे आपके लिए रास्ता हो जाएगा काफ़ी आसान। और नहीं सीखोगे तो फिर से सीखनी ही पड़ेगी कभी ना कभी, तो बच के भैया नहीं जा पाओगे। तो ऐसा करो कि हम सीख लेते हैं आसानी से, और इतना आसान बना दूंगा मैं, इतना आसान कि इसको सीखने के बाद, इस क्लास को अटेंड करने के बाद आपको कभी कहीं कुछ देखने की ज़रूरत नहीं पड़ेगी, ये मेरा वादा है। और एक बात और बोल दूं, जिस तरीके से मैं बता रहा हूँ ना, आपको कहीं एक्सप्लेनेशन नहीं मिलनी, शायद शायद कहीं मिल जाए, शायद। ठीक है ना? तैयार हो? So the topic that we have taken is wave function itself. We will look at it, how it comes into being, okay, from basic concepts, basic observations, okay. Now we will take the example of a string and how it all comes into picture. So we have a string tied on both ends. This is a side support and another one on this side. Now take two scenarios. First we have stretched the string in this manner, and we will have another situation where the string is stretched even further, right? So we have situation A and situation B. Now let's draw the midpoint here. Now you will notice that from your observation only I am talking about, yeah, you will observe that if you pull a string too far away and let it go, what will happen? It snaps back much more quicker than the case where you have not stretched it that far. What I am trying to say here, the further you stretch the string away from equilibrium, the quicker it tries to revert back to the original shape, right? So in case A, we have stretched the string much farther away compared to the case B, and common sense tells us, right, it's common sense that string A will accelerate much faster, right? It will try to revert back much more quicker, much more force will arise here because the stretching is much larger, right? From Hooke's law, what do we have? More the stretching, more the extension, more is the force, right? So the first point that we have is from Hooke's law. that force, restoring force is proportional to minus of change in length, isn't it? This is the Hooke's law. So, the acceleration of any point in case A is greater than in case B, okay? That has to be true. Now, in fact, we can look it at in a slightly different manner, okay? What is that? That you will notice here that curvature of situation A that we have, string this one, okay, the yellow one, the yellow setup, okay, is greater, right, at every point. Curvature is greater, right, it is curving more. So, what I can say that curvature in situation A is greater than in situation B, isn't it? Curvature in situation A anywhere is greater than in situation B. Curvature, what does that curvature means? Something that is curving, right? So, this is flat, right? This is flat. This is slightly curved. This is even more curving, right? Flat, slightly curved, much more curved, right? So, curvature, what do we have here? Curvature in case of A is greater, and curvature is greater, and also acceleration is greater in that case. Can you see the point? Let me repeat it. In case A, because it has been stretched much farther away, it will snap back much faster, much more faster than case B, and hence it will have more acceleration from Hooke's law. But observation also tells us, what does it tell us? It tells us that curvature of string in case A is greater than in case B at each point. At each point, that is what we will say. In general, it is true. Okay. So, let us just take the brighter color. That acceleration of any point on the string is also proportional to curvature. That is what the observation is, isn't it? That is what we have. Now, acceleration that we have, acceleration in general, A, we write it as, in this case we will write it as d square y dt square. Okay. I am using symbol dou because y in case of string is a function of both x and t. Okay. It is a function of both x and t. So, that is why we are only taking the derivative with respect to time, because we are talking about acceleration, right. And curvature let's call it k. We haven't used k anywhere, right? Yeah, okay. From maths you would know it is given by d square y by dx square mod of it divided by 1 plus dy by dx sorry, I will use the different bracket square to power 3 by 2. Okay. So, that is what curvature is given in differential form. Yeah, you have learned this in physics also, and in maths also you must have learnt it. Okay. Anyway, so this is a general formula for curvature. Now, what do we have here? For small stretching, that is the ideal case, ideal wave motion. The first derivative can be taken as approximately equal to 0. Why? Because you see, go back, we are not, ideally we do not take it too far away. The stretching that we have here, no, the stretching that we have here, we do not really, I have shown it all in an exaggerated sense, but in reality the stretching that we give, the pull that we provide to the string is not that much, because if you stretch it too far, the behavior is not same as that of an ideal wave. Those waves are difficult to deal with. So, we talk about only cases where that distortion is not too much, yeah, the string does not get too distorted. In that case, the first derivative is actually, it can be shown easily that it is very close to 0. Okay. If it is only slightly tilted, look here, if it is only, if this is the flat surface and you just do it this much, then slope will be close to 0, right. In this case, the slope is at different points are very large. For example, the slope, this is almost 45 degree, isn't it? Almost 45 degree. Here almost 45 degree. But if you just do it little, it will be like few degrees only, few degrees only. Okay, these are few degree angles. So, we are talking about this kind of waves where you only distort it slightly. That is the ideal situation that we want to deal with, and hence we can approximate the first derivative to be 0, and from here we will get that comparing that acceleration is proportional to curvature, you get d square y by dt square is proportional to d square, just a minute, sorry, again I made the same mistake. We will use partial derivatives, d square y by dx square, and this becomes, when you introduce the proportionality constant, which turns out to be something like a positive number, here also into correction, is given by equal to c square d square y by dx square. Now, this c square has been introduced from experience only, you can assume that, and c is in fact nothing but speed of the wave. Yeah, okay, the line is jumping around. Anyway, so this is what we have. Now, we will look at the solution of it. In maths, you will be given some solution. General solution of this one is what we study in greater details, and in the solution in this case turns out to be of the form yxt as a cos kx plus minus omega t. In general, this is what you get, okay, in this case.